Let me start by thanking the organizers for this kind invitation. Let me start again.
Just let it roll.
There you go.
Yeah, we'll trim it.
Let me start by thanking the organizers for their invitation. And it's really a great pleasure to be able to join you on this wonderful occasion.
So I think what you want to do is like, say hello or something first, right? Hello, and
Okay.
and then the thank you thing.
So no particular need to stop it, you're
No,
thinking,
yeah,
right? Just
yeah.
let it roll.
Because then I have to wait for the cycle, right?
Okay. Well, let me start by thanking the organizers for this invitation. It's really a great pleasure to be able to join you on this wonderful occasion and share some of our thoughts with you. Next. So let me start by explaining what I mean by p-bits. Now, bits is something we are all familiar with. That's this basic thing in digital information. These are things that are either 0 or 1. This binary information is represented in terms of bits. And you could, in hardware, you could represent it. Let me start over again.
Okay.
Yeah.
Go ahead, just
Oh,
roll.
let it roll, doesn't really matter. Can you go back then?
Oh, yeah, then you just do this.
Ah,
Yeah,
okay,
sorry.
good. Good. Let me start by thanking the organizers for this invitation. It's really a great pleasure to be able to join you on this wonderful occasion and share some of our thoughts with you. So what do I mean by p-bits? Next. Well, we are all familiar with what bits are. That's these things that have two values, 0 or 1. And that's how you represent digital information. Now, at the other extreme, we have what are called qubits, which are the basic things in quantum computing. And these are represented by single spins, which can be the superposition state of 0 and 1. And earlier today, you heard Professor Ashalam talk about qubits. Now, p-bits are something in between, in the sense that they are very classical objects, but these are things that are not 0 or 1, but keep fluctuating between them. So next. So how would you implement them? Well, one way to think about it is the way you can represent bits. One way to represent bits is stable magnets. Magnets are also spins. It's just that their internal interaction makes all the spins line up in a particular direction. And there's usually an easy axis. So when they're lined up in a particular direction, there is an energy minimum which keeps them there. On the other hand, you could switch it to a different state, which is also an energy minimum, a local one. And usually, once you put them in one of these minima, they would stay there for a long time. And people try to engineer this barrier in between so that it's like 40 or 50 kT or more, so that the information stays for many years. Now, a well-known problem with magnets is that often the barrier is not high enough. So you have something like this, in which case once you put them in one of these states, it doesn't stay there very long. And depending on the height of this barrier, like if the barrier is say 20 kT, then it might stay there only for say microseconds. And if you made it even smaller, they would stay there even for shorter periods of time. And so they would keep fluctuating between 0 and 1. And that is what we would call a p-bit. And usually, of course, these are what you would call bad magnets, and it's considered a problem. And what I've been trying to argue is that this problem actually in a way represents an opportunity, that you could use these fluctuating things, these p-bits, to do useful work. Next. So that's what I really want to talk about, these unstable magnets which can represent p-bits. And one point I should mention is, there's this famous paper of Feynman that inspired a lot of the work on qubits, But in that paper, before he goes to quantum computing or qubit, he actually talks about probabilistic computing somewhat. But while the quantum part has attracted a lot of attention, the probabilistic part is relatively less appreciated. Now, this is what we could call something as in between bits and qubits. And the point is that these are classical things which are robust, can be built with current technology, they would work at room temperature. So it's worth asking what kind of things could you do with these p bits, because even if they could do, say, 10% of what we expect from qubits, it's still worth the effort, because these are room temperature things that can be built today, and these could be part of everyday life. It could be part of this Internet of Things, for example. Okay. Next. So let me point out that these p bits are also in a way connected to another vast area of neuromorphic computing. Again, something you hear a lot about these days. So if you look at neural networks, look at Google neural networks, the common picture you'd see is something like this, that it takes a bunch of inputs from different bits, combines them, forms a weighted sum, and then it drives, there's this threshold element which looks at this weighted sum, and if it is big, it goes to 1, if it is small, it goes to 0. And by the way, I put the 0 in quotes because with magnets, I guess the magnetization is +1 or -1. So when I write 0, I actually mean the -1 state. You'll also notice I've called this synapse and neuron, and those are within quotes because I guess when you think of biological neurons, they are much more complicated things. So I'm told that often people who know about biological neurons, they think this is too simplified a picture of that. But in this artificial neural network world, you'd often think of that as the neuron and this as the synapse. Now, when it comes to p bits, it connects to a small subset of that area, of this whole area of neuromorphic computing. Next. And that is where you might call this stochastic neuromorphic computing, in the sense that instead of a threshold element like that, you have this what you call a binary stochastic neuron, in the sense that when the input is large, it goes to 1. When the input is small, on this other side, it goes to -1. But when it is 0, it doesn't really go to 0. What it does instead is it fluctuates between +1 and -1, like the p bits that we talked about, and such that the average value will kind of follow that curve. So it's the average value that follows that curve, but the basic neuron always outputs a +1 and a -1. It's just that it does it probabilistically in such a way that the average value follows this curve. Now, mathematically, you could describe it with an expression like this, where this SGN means it's the sign of what's inside. So what's inside, if it's positive, you get a +1. What's inside, if it's negative, you get a -1. And when I write rand, what I mean is a random number distributed evenly between -1 and +1. So it may not be obvious, but if you think about it, I think you can convince yourself that that expression mathematically describes something like this. Okay. Now, so this is what we'd call a binary stochastic neuron. Now, and if you combine that with a synapse, then we can do all kinds of useful things. And there's a lot of work in this area where these are implemented in software, in the sense you write MATLAB codes or software codes to mimic those two equations. But what we are interested in with p bits is hardware implementation of these things. So in software, of course, this M and I, this output and input, those are dimensionless quantities. Now, what we'd like to do is build circuits where those are actual voltages, which can drive another in a normal circuit fashion. So how do you convert something like this into a voltage? Well, that's where the magnetic tunnel junction comes in. Next. You see, one of the things you have heard several talks on at this symposium is about this device called the magnetic tunnel junction. In a way, that's probably the only real spintronic device, which has found important applications. And there's a technology developing on what are called MRAMs and embedded MRAMs. And here the basic device is the magnetic tunnel junction, which consists of a fixed layer which has a fixed magnetization and a free layer whose magnetization can be in one of two directions. And that's what represents the 0 and the 1. And if the two magnetizations are parallel, then the resistance is low, let's say 5 kilo ohms. On the other hand, if they're anti-parallel, the resistance is high, let's say 15 kilo ohms. So it changes between those two resistance values. And if you put that in series with another resistor, which let's say has a value of something in between the two, like say 10 kilo ohms, then you would have a potential divider circuit like this. And what you can show is that when this resistance is low, that's when the voltage in between at this node will be closer to the upper one, whereas if it's 15, then it will be closer to the lower one. And so the voltage here will change depending on whether you store a 0 or a 1. So this device kind of converts this magnetization into a voltage. And this is a device, as I said, is getting a lot of attention. It's the basis of this whole technology that you hear about. And here I have shown an in-plane magnetization. Some of the work involves what are called perpendicular magnetizations, but the basic principle is exactly the same. If the magnetizations are parallel, resistance is low, anti-parallel, resistance is high. Next. Now, if instead of a stable layer here, which stores a 0 or a 1, we had one of these unstable layers, one that fluctuates between 0 and 1. Then what would happen is, if you looked at that voltage, it would also fluctuate. And so you'd have this noisy voltage, you see, just like what you need to implement this binary stochastic neuron. You'd have an output voltage that was fluctuating. Of course, we also need to be able to control it with that input voltage. That is, what you want is this thing fluctuates, but then if I put a big positive voltage here, then it should stop fluctuating and take on one of those values, like +1. And if I put a large negative voltage, it should go to -1. So we kind of need that 3-terminal thing to control it. So how do you do that? Well, one way to do it would be, next. So one way to do it would be to use this spin orbit torque. The idea that if you use a heavy metal, one with this high spin orbit coupling, and you inject current into it, then you can inject spin currents into that unstable layer, and the spin current could help pin the magnetization. So that's one way to do it. Now, what I'd like to talk a little more about is what we think is a simpler way. Simpler way in the sense you don't need to introduce this new physics, this physics of high spin orbit materials and the spin orbit torque and the pinning. Instead, you could just use existing devices and existing physics. Next. So here the idea is that you just take a regular MTJ, the ones that, as I said, is the basis of this embedded MRAM technology, in series with a transistor. And only difference being, of course, in the actual technology that people are developing, they want stable MTJs because they are trying to store information 0 and 1. But of course, one of the problems, as I mentioned, is you get a lot of bad magnets, junk magnets, which you have to throw away. And those are the ones that I am arguing could be useful for what we are talking about to implement p-bits. So what we want is these unstable magnets whose resistance fluctuates here, and as a result the resistance here also fluctuates, and what we are looking for is a way to control that fluctuation with a third terminal. And the point is, and that's what was shown in this paper, that this gate voltage of the transistor could help you do just that. And how is that? Well, the thing is, as you know, a transistor is basically a controlled resistor. Now, if the resistance of this transistor is say 10 kilo ohms, something in between the 5 and the 15 of the MTJ, then you get a big fluctuation here. In the sense, when it's 5 kilo ohms, the voltage changes quite a bit from when it is 15 kilo ohms. But supposing we turn up this gate voltage so that this transistor turns on and the resistance is much lower, not 10 kilo ohms, but let's say 1 kilo ohm, then you see that voltage won't fluctuate very much anymore. I mean, that can be 5 or 10, doesn't really matter. As long as this is much lower, this voltage would be kind of pinned to the lower voltage. And again, if you change the gate voltage so that this becomes 100 kilo ohms, then again that voltage won't really change very much. Whether this is 5 or 15 doesn't matter too much. So thus, you could use this gate voltage then as this third terminal, the one that controls this fluctuating voltage. Next. So this is something we simulated properly. So that what I described to you is the intuitive idea of why we thought this might work, and we simulated it properly using the standard models for 14 nanometer FinFETs and the usual LLG equation that is used for stochastic MTJs. And what you can see is that the output follows the input in the way we want it. Namely, if the input is large negative, then it gets pinned to the negative value. If it's large positive, it gets pinned to the positive value. And in between, it fluctuates between +1 and -1. So it gives us this 3-terminal p bit that we need. Next. And what we showed is that that curve again can be mathematically represented something like this, where you have these circuit quantities, this input voltage and output voltage, but which are normalized to certain parameters of the circuit to give you the dimensionless numbers, which would usually what you'd use in software simulations. But the point is, overall then, this circuit will give you this stochastic binary neuron. Next. Now, in order to do useful things with it, though, you also need the synapse. You need a way of taking outputs from many other neurons and feeding it into the input of one of them. Now, adding currents is usually easier, in the sense currents naturally add, whereas adding voltages is a little trickier. And here you need to add voltages because these are high input impedance devices. But one way to do it, and there are other ways too, one way to do it is, next, is to have a sort of capacitive divider. So you have these capacitors, so the inputs from other neurons come in here, and what you get at the input to this neuron is a weighted sum of what you apply to these inputs. So that's what this weighted sum is, what would appear here. Instead of capacitors, you could also use resistors, and mathematically, almost the same equations describe it. And in either case, what you'd get is a voltage here that is a weighted sum of what came in. Now, one good compact way of doing this is, next, is this floating gate MOS, which again is a well developed technology, where there is widely used also. And that is, there's a floating gate, and then you have these inputs that come in through these capacitors. And one of the earliest references I found for these things is paper by the late Professor Omi, who was also actually at Tohoku University. But these structures then, this floating gate MOS, could be combined with what I described as this binary stochastic neuron. And together then you have a unit that could take inputs from multiple neurons and then perform this function that we need. So this is the unit that I'll represent with that icon. Lots of number of inputs coming in, and then there is an output. And the reason I need an output with both a positive and a negative, that is what we are doing with these inverters, with this second inverter, is reason you need that positive and negative is because to implement useful functions, you often need negative weights. And of course, this capacitive network weights your inputs, but will only give you positive things. So, if you want a negative weight, you have to take the output from the negative output here. Next. Okay, so rest of the talk then, let me try to explain what you could do with it. So far I have been talking about how you could build one of these things, something that would have this character of this binary stochastic neuron. Let us talk about why you would want to build it, what would you do with it. And then let me first note that in general with these neural networks, the way you do different types of problems, different types of functions is by designing this weight matrix. That is how you weight the different inputs in order to obtain your output. So, that is where all the thinking goes in terms of the specific problem in mind. Next. So, I will talk about a few different applications briefly to give you a flavor of the kinds of things one could do with it. And as I said, this general area of stochastic neuromorphic computing, there is a lot of work, and much of it is though software based. And one of the differences between software and hardware is that in software you can easily implement analog weights. So, you could have a weight of say 1.2315. But when you do it with hardware, then usually it is better if you had a few distinct quantized values. So, for example, if your weights were 1, 2, 3, 4, then you could easily implement them, because when you want a weight of 1, you could connect that particular input to one input only. If you want 2, you could put it on 2 inputs, assuming all the inputs are identical. So, if your input goes into 2 of them, you will get a weight of 2. You put it into 3 of them, you will get a weight of 3. Next. And so, this hardware, what it naturally provides is quantized values of this weight matrix. And so, the applications I will try to talk about, those would be examples where you could do it with a limited number of quantized j values. Okay. Next. So, let me start with something that is often referred to as Bayesian networks, and this is like the paradigm for Bayesian networks. That is, you have these what are called the child nodes who are influenced by their parent nodes. And the thing is, it only works one way. The child is influenced by the parent, but the parent is not influenced by the child. And as I mentioned, and I have used this example because it is easy to relate to the kind of problems we will talk about. On the other hand, it can be representative of many other types of problems of interest also. For example, you could be interested in say medical diagnosis, in which case a particular symptom could have many causes. Of course, in that case you could have more parents. I mean, you need not have just 2 parents. Like you have high blood pressure, that could be due to multiple reasons, for example, etc. But all of those could be mapped into things like this. You have child nodes which are influenced by parent nodes. And how do you simulate this with a circuit? Well, each of these nodes becomes one of these units that I talked about. And so, you have the father node then influencing this child, and the mother node also influencing this child, and similarly this child is also influenced by both. Now, the question you ask is, what is the genetic correlation between the 2 children? And this is a result, again, if you wanted to calculate it, you could use Bayes' theorem, but this is a well known thing that if you just Google like what is the genetic relatedness of 2 siblings, you would find that the answer is 50%. And what I would like to show you is that this circuit also gives you that, because what you could do is, next, what you could do is look at the output from the 2 child nodes and correlate them. So, what does it mean to correlate? It means you take a product of the 2 and integrate over a long period of time. So, you are doing a time average in order to come up with the average that you would have got over many genes. That is the genetic relatedness. Now, how do we do this product? Well, you could do it in software, but you could just as well do it in circuits as well, because when you multiply two things, the digital gate that will do it for you is the XNOR gate, in the sense that these are binary things. So, if both are -1 or both are +1, then the answer should be 1. So, here you can see the XNOR gate is just like that. If both are -1, you get +1. If both are +1, you again get +1. But if one is -1, one is 1, then when you take the product, you get -1. So, XNOR gate effectively multiplies these two binary things. And how do you average it over a long time? Well, you just use a long time constant RC circuit. And so, if you looked here, what you would get is the correlation between these two child nodes. Okay, next. So, what we did was, so here what I am showing is again elaborate circuit like this, where there are two pairs of parents, and two of them here are siblings themselves, in the sense that the grandparents are common for them. So, now if you look at the correlation between, say, two children, you can see you get 0.5, and these are traces that are coming out by just looking at that voltage. So, you are just on an oscilloscope, or this is all done with SPICE, these are all simulated in SPICE, and you are just looking at that voltage. So, the capacitor was initially uncharged, and then it goes up to this 0.5. And if you look at the correlation between a child and the parent, for example, this C2 and M1, that is also 50%. And again, these are things you can Google, genetic relatedness of child with parent, for example. Now, this 25%, that is what you get when you correlate, say, a child with an uncle, in the sense it's the parent's brother, and then you get a correlation of, say, 25%. And there are other different possibilities one can actually do, and the circuits give exactly what you would expect based on Bayes' theorem, which, as I said, these are well known results you can easily look up. And of course, if you have unrelated people, then there is no correlation, it is just 0. Okay. So, this is an example of what I would call a genetic circuit or a Bayesian network. Next. Now, for genetic circuits, it seems natural that you can represent it with these P circuits, because after all the quantities you are dealing with are probabilistic. But next I would like to show you an example that you can use these probabilistic circuits even to do deterministic things, where actually you are looking for deterministic answers. In fact, when you implement it this way, you will see you get some additional features that you do not get in the normal way of implementing these things. So, just to illustrate the principle, if you had two of these which were totally unconnected, then this one would fluctuate between 0 and 1, that will fluctuate between 0 and 1. So, if you look at the composite thing, you have these 4 states, both 0, 1 0 1 1, 1 0 and 1 1, and the system would go equally among all 4 states. Next. But supposing I now connect them so that the negative output of this goes to the input of that, and same here, vice versa, then what happens is the two get anti-correlated. When one is 1, the other wants to be 0, and when the one it's 0, the other wants to be 1. And so, instead of these 4 things being equally populated, you now have these 2 things that are populated only, 0 1 and 1 0, and that would be kind of like a NOT gate. Here I am showing both populated, but if you fix one of them to be, say, 0, then the other would be 1. So, that's how you get the NOT operation. Another possibility is, next, you could do the copy operation, in the sense you take the positive output of this and feed it there. That way the two want to be the same. So, in this case you will find it will go to 0 0 or 1 1, but it will avoid the 0 1 and 1 0. So, this is just to give you a rough idea how these work, but next let me show you more non-trivial gates. Next. So, this is an example of a gate, this includes one of the gates we talked about, the XNOR, where A and B are the two inputs, and that is the XNOR gate. And then I have also put down the outputs if you had an AND gate, and then also the outputs if you had an OR gate. So, how would you implement something like this? Well, what you can do is, if you interconnect all of these various nodes, each one of these would become a node in our P circuit. So, there would be one of those blocks representing each one of these. So, there is 5 of them, and actually you also need a hidden one, this is the H. So, there will be 6 of them, and then this is kind of the interconnection matrix or the weight matrix. So, this describes how they will be connected. And so, how did I come up with this matrix? Well, that is what I will not go into in this talk, but there are training algorithms available, and we have also used a different method that is kind of more analytical. It is based on linear algebra, which is described in this paper. So, the point is, given this truth table, you can translate it into a connection matrix. And once you have the connection matrix, once you have the connection matrix, what you can do is have these blocks. Each one of these represents one of these, and then according to the connection matrix, you can connect these up. So, for example, what it tells you here is the output of H should go to XNOR and OR with various weights, and that is what I have showed here. It goes to OR and with a +1 weight, and to XNOR with a minus weight. So, according to the different columns, that is how you connect them up. And once you have connected them up, now if you look at the outputs, what you will find is, you see, now I have got 6 of these p bits. So, how many states are there? Well, 2 to the power 6. Each one can be 0 or 1, but it will only visit 4 of those and avoid all the other ones. Which 4? Well, the ones that are allowed by this truth table. See, truth table meaning, you see, if you look at 0, 0, 1, 0, 0, in decimal that is 4. Similarly, 1, 0, 0, 1 in decimal that is 9. This is 17 and this is 31. And so, when it jumps around, you only see those specific values being picked up, and anything in between it avoids. And we are actually not looking at the hidden one, H1. So, there is only this 5 visible one that you are looking at. So, I should have said the possibilities are 2 to the power 5, that is 32, but it is picking up those 4. And if you create a histogram, you will see peaks at 4, 9, 17 and 31. Now, you could also operate in a normal gate mode, where you give it an input and look at the output. So, next. So, supposing I fix A at 1 and B at 0. Okay, so, that singles out this line. So, how do I fix it? Well, I put a big enough voltage, so it is forced to be 1 or forced to be 0. And now you see I get only one peak, that is this 17. What that means is, if I looked at the XNOR bit, I had got 0, AND would be 0, OR would be 1, exactly as required by the truth table. But the interesting thing about doing Boolean gates in this way is, it also works in reverse. That is, in Boolean gates, you always put an input and get an output. But here you could actually fix an output and then ask what inputs could have given you that output. So, for example, next, supposing I were to fix the XNOR gate and say that XNOR is 0. So, give me all possible ways in which I could get a XNOR output of 0. Well, now you see it does not single out a particular line, instead it singles out both these lines. And so, when you actually look at the output, you get 2 peaks, 9 and 17. So, it jumps back and forth between those 2 possibilities. And so, usually when there is a unique possibility, it gets it very quickly at speeds that are determined by the CMOS. Whereas, when you have multiple possibilities, then it takes a little longer, because it is jumping back and forth between them, and the time is determined more by the magnet time, the time that it takes for a magnet to switch back and forth. But the amazing thing here is that it actually works in reverse, and so allows you to do many other types of problems that you could not do if it only worked forwards. Next. For example, you see there are many cases where the direct problem, say adder or multiplier, is relatively easy, whereas if you think of the inverse problem, that's a hard one. So, for the adder is you give it a and b and it gives you the sum, but then there is this subset sum problem, which is like I give you a sum and ask you, what possible things could have got you that sum, etc. That is considered a hard problem. Multiplier, I give you 3 times 5, you get 15, but I could give you 15 and ask what are the factors of 15, and that is a very well known hard problem. As you know, it is one of the problems that motivates a lot of the work on quantum computing. And these are things again we have done with simple things where you have a few p bits. Whether it scales up to big problems, we will have to see, the inverse ones. On the direct ones, we have also done big problems, 32-bit adders and so on. Next. Now, before I move on, I guess the other thing I should mention is that if the weight matrix is symmetric, that means when there is a connection between 1 and 2, there is also a connection between 2 and 1, then these probabilities actually follow a Boltzmann law, and that is why these are often referred to as Boltzmann machines. See? And there is an energy function which actually gives you all the probabilities. And this is the idea that translates into this, that allows us to use these Boltzmann machines for optimization problems, because optimization problems usually have a cost function, something that you are trying to minimize. And in statistical physics, of course, energy is the cost function. So, what you could do is, given a particular problem like say the traveling salesman problem, you could map it into a symmetric network of this type such that the low energy solutions would actually represent the correct solutions that you are looking for, ones that minimize the cost function. And I should mention that one of the properties of these things is that I have shown these unwanted things having some probability, much lower than this one, and the ratio of the wanted to the unwanted is determined by the ratio of their energies. Now, if you made the J matrix, this weight matrix, say 10 times bigger, then what would happen is states whose energy were say 2 and 1 would now become 20 and 10, and now the ratio of their probabilities would be much larger. So, if you turn up the weight matrix, you can actually discriminate very strongly against the unwanted states. But then if it is too high, the problem is often that you tend to get stuck in metastable states, just as in regular statistical physics. And so, there is a trade-off there on the magnitude of the J that you would want to use. Next. Now, let me just make a couple of comments about another application of things like this, which is much more common, and that is image recognition or say character recognition, where you have a set of characters like this and you want to recognize them or classify them, that these should be 0, these are 1, this is 2, this is 3, etc. And the point I want to make is these problems can also be viewed as a truth table problem, in the sense that if you look at one of these images, it has 28 by 28, which is 784 pixels. And if these are black and white images, those are plus 1s and minus 1s. So, you have 784 of these, that is the input, and then the output is, okay, is it 0 or is it 1 or is it 2 or is it 3? And so, those are the 4 outputs. So, in a way you could write a truth table, and every image is like a line of that truth table. And so, the same methods we were using for getting a network to recognize the truth table, you could use it for character recognition and image recognition. And we have done some of these problems. Next. And we again find that once you train it with these images, yes, it can recognize the training set. But one of the challenges, of course, here is that if you train it with certain images, question is, can it recognize something that's a small variation of those? And that's where many of the modern algorithms are amazingly powerful, and those are things we are working on at this time. So let me now summarize again. Next. What I want to tell you about is this concept of p bits, that's somewhere in between bits and qubits that you hear a lot about. And as I said, these p bits are a little like this binary stochastic neuron that forms kind of a subset of that field of neuromorphic computing. And a very natural way to implement the binary stochastic neuron is by using this embedded MRAM technology, where you have a transistor in with an MTJ at its drain. But the only difference being, in that technology, you are usually trying to build good MTJs, which store 0 and 1, whereas what we want here is the bad ones, which fluctuate between them. Next. And you could combine that with floating gate MOS, and here there are many other options also. This is just one of the options, in order to get what you might call a weighted p bit, where a p bit with a synaptic element at its input, which adds up things. And this is what we represented with this icon. And what I tried to show you is, using this basic building block, you could do many interesting problems. Next. And I just went through a few of them. As I said, this is a vast area in itself. There are many applications people have looked at. But the big difference, of course, that we have to be careful about is, when you're doing it in software, you can implement any weight, whereas in hardware, usually you have a limited range of weights. So you have to see whether the applications would work under those conditions. And I'd like to stress again that all the results I showed were actually not just done in MATLAB or software, but these are SPICE simulations, where it's where we have using state-of-the-art models for the hardware, for hardware like this, for floating gate MOS or for this NMOS transistor in series with a MTJ. And these are the details if you're interested. I hope you find this interesting, and the details if you're interested. Next slide. I have listed them here, and this is, I guess, ongoing work. So we expect to be looking at different applications in future. Thank you.
Okay.
How did I do on time? Are you actually, I was getting worried that I might.